Welcome to Volcano Notes Part 2. And just like as if we were doing the first part, if you should be having your fill in the blank notes and you should be working through these notes. Are these notes intended to give you a complete background information on volcanoes? No, but they're going to give you a lot of good information that you're going to need to know for our assessment at the end of the unit. And these notes will also help get you through a lot of the activities that we're going to do in class with volcanoes. And as always, if you have any questions about these notes, if you want to talk about anything further related to these notes, if there's some confusing parts or you just want to learn more, just talk to me in class. I'd be happy to sit down and we can talk about volcanoes. Now, we ended up part 1 talking about hotspots. What we're going to do now is we're going to get into the different types of cones. And there's 3 main types of cones or volcano types that we're going to talk about. And the first one is called a cinder cone. And a cinder cone, let me back up once here. Oh, kind of put one of the slides out of order. But a cinder cone is actually a steep conical hill. And a cinder cone is comprised of pyroclastic material. Pyroclastic material, these are the fragments of volcanic rock that come spewing out of a volcano, thrown out of a volcano. And they tend to cause a lot of volcanic explosions. They tend to be pretty explosive. And these cones can range in size anywhere from tens to hundreds of meters tall. So cinder cones, they're going to be very, very small ones, and they're going to be larger ones, but these are not nearly the largest cones that we have on our planet. So this next slide, excuse me, but here we go. So we're back in order. So here you see a cinder cone. Cinder cones tend to be pretty steep sided because of the material that they're made out of. Here you can see some of the cinder cones being created, and I like this one down here. What does this remind you of? Anybody have an idea? If you were thinking this kind of reminds you of an anthill, that's exactly what I was thinking about if you look at what ants do. So this would be a cinder cone. And here you see a cinder cone being created. It's the same picture in both, but it almost looks like it's dirt. Looks like dry material. So here you can see that it's molten, and as it comes up, as it's in the air, it cools off. So by the time it lands, it's already a small piece of rock or ash. One of the most famous cinder cones in recent times is percutine. And percutine actually has a rather interesting history. In 1943, it erupted for the first time, or was, I don't want to say if it erupted for the first time, you just want to say it was erupted for the first time, but it was born in 1943. And the story has it that a farmer was in his cornfield, and he noticed there was a crack in the earth, and out of that crack was coming some gas as well, and eventually it was not only gas, he also noticed some ash was coming out. And when the farmer came out to the field to check it out the next day, that ash that had been coming out actually grew to about 40 to 50 feet high. And over the course of 9 years, percutine actually grew to about 1,300 feet high. So one of the reasons why this is so interesting, because it happened in 1943, once it started happening, geologists from all over the world went there to watch, because they were actually watching the birth of a volcano. They could actually watch and study the volcano from the time it was born till it stopped erupting 9 years after it originally started. And percutine today is considered to be not active. They don't think it's going to erupt again. And it grew to be quite large. In fact, some of the pyroclastic material actually buried a nearby city, town. So just a little interesting side note there. So here we can see another picture of it. So because it happened in modern times, there's a lot of people studying it. And you can see all the ash, all the material coming out of the top of percutine. And again, it erupted for 9 years and got to be quite tall. Covered 25 square kilometers. Now, a second type of volcano that I like to talk about is called a stratovolcano or composite cone. A lot of times I like to call them composite cones or composite volcanoes, but if you ever see the term stratovolcano in a geology book or in a like a Nova Special on volcanoes, they basically mean the same thing. And these volcanoes tend to be steep-sided, and they're built by eruptions not just of pyroclastic material that you saw with cinder cones, but there tends to be alternating eruptions of pyroclastic material as well as lava. So they tend to be layered. And they may erupt a variety of different magma types, including basalt, andesite, and rhyolite. All but basalt commonly generate pretty highly explosive eruptions. So here we see a side view or a cutout of a composite cone. So you can see the different layers. So here they're labeling the pyroclastic material as well as the lava flows. So they tend to alternate. And that's why they call it a stratovolcano or a composite cone, because it's composed of both. A really good example of a composite cone here in the United States is Mount St. Helens. You might say, well, that doesn't look like Mount St. Helens. Well, when I was a kid, this actually was what Mount St. Helens looked like. You can see that it looks like a pretty standard volcano. But in 1980, something happened to Mount St. Helens that changed its appearance. So if you look at Mount St. Helens today, or if you've been to Mount St. Helens, it looks very much different. And that's because this happened. A bulge on the north side. Scientists notice a bulge forming on the north side. And why, you might ask, was a bulge forming? Probably because there was magma that was starting to pool up behind it. And there must have been a weaker spot in that part of the volcano, so that's the side that started to bulge out. And in 1980 in May, a landslide occurred. And what happened with the landslide, scientists believe because there was a landslide, and, oops, sorry, let me get that pen again, there we go. Because that landslide removed a lot of the mass that was above that bulge. Once that land was removed, it no longer could hold back the pressure of the magma and the gases and everything that was in the magma that was inside the volcano. And as a result, there was an eruption. Now, normally you have eruptions coming out of the top of a volcano. But because of that landslide, and you can see the landslide here, you can see it coming down. Because of that landslide, we actually had something called a lateral blast. And you can see it best probably in this picture here, where it's not necessarily going straight up, but it's actually shooting out of the side. And as a result of this lateral blast, so here you can see the lateral blast. So on the back side, you can see the whole volcano. It's there. So it did top, but this whole side is missing. And as a result of this lateral blast, there's actually people that lost their lives that were there studying Mount St. Helens because they had a pretty good idea that it was going to erupt. There was small earthquakes that are commonly associated with volcanic eruptions that were happening. So they knew something was up, but they had no idea it was going to be a lateral blast because there was a young geologist. He was 30 years old. His name was David Johnson. He worked for the USGS, United States Geological Survey, and he was there monitoring it, taking data, and he was in an area that was considered to be a low-risk area where if an eruption occurred, he should have been fine. But because it was a lateral blast, he happened to be on that side that the lateral blast happened, and as a result, he lost his life. And 56 people total died as a result of it. And not all of them because of the volcanic eruption. He probably died pretty quickly, but a lot of it was because of the mud flows that happened as a result. So, did Mount St. Helens put out a lot of ash? It certainly did. You can see here's a map of the United States where if you look down below here, the yellow, this is you have a trace of ash up to a ½ inch. So you can look, here's Washington, you've got Montana, you've got your North and South Dakota, as far away as Minnesota, they could find traces of this ash. So halfway across the country. In fact, they actually found some in Oklahoma. And this is an odd phenomenon because there's this huge space in between that there was none. And I'm not sure if it was the jet stream was positioned just right, but enough of it must have got into the atmosphere that they found traces of it in a wide area of Oklahoma. But if we get closer, we can see 2 to 5 inches. So here in Wisconsin, we're used to snowfall, and you can imagine how much snow it would take to get 5 inches, and how heavy that snow can be if it's a wet snow, especially if it's on your roofs. But take a look at this photo right here. This was the cloud of ash. And so instead of snowing, it was, or I should say, instead of snowing snow, it was actually snowing ash. And so here are people taking all this ash and they're moving off to the sides, and it's basically like they're shoveling their driveways, they're shoveling this off. And especially if you got it on the roofs. Now, I don't see any ash on these roofs here, but if there's ash up there, people would have to get that off pretty quickly, because once it starts to rain, that's going to start to set up. It's going to be hard like concrete. It's going to have a lot of mass. And there were lots of reports of buildings collapsing because the roof could not hold up the massive weight of all this ash. And another interesting thing that happened with Mount St. Helens is there was snow on the mountain. So once the volcanic eruption happened and all that hot gas and that magma came out, a lot of the snow melted instantly. And as a result, along with all the ash, it rushed down the side of the mountain, creating mud flows. So here you can see tall trees just totally wiped out. Huge tracts of forest wiped out because of this mud flow. And here's a more recent picture, August 2005. Back in 2005, Mount St. Helens was actually very active again. Now, it was active after it erupted, but here you can see the cone starting to rebuild itself. So if this continues to happen, eventually Mount St. Helens, might get back up to where it was in the past. And back in 2005, we were watching it pretty closely. I mean, it was on TV, it was on the news quite a bit, because scientists were fearful that it was going to start being active again, and that there might be some more major eruptions being, on the near horizon. But it was in the news for a couple of weeks, and it started to die down. And we're not necessarily talking about a major eruption anymore coming out of Mount St. Helens anytime soon. Another type of volcano is a shield volcano. Shield volcanoes are actually the largest volcanoes in the world. They tend to be the largest mountains in the world as well. They're basically made out of basaltic materials. That's the type of lava that's there. They tend to be low angle type cones. For example, if you wanted to simulate the creation of a shield volcano, what I would say is take some yogurt. Take several containers of yogurt and just dump it out on the table. And as you dump it out, dump it one container of yogurt right on top of the other. And as you can see, it's not going to necessarily get really steep. If you dump the yogurt out one on top of the other, on top of the other, on top of the other, it's going to spread out. It's not going to be very tall, but it's going to be very massive as far as how wide it gets and how much land it will cover. And that's the same thing with a shield volcano. They tend to cover a lot of area. Now, again, like I said earlier, the largest volcanoes on Earth are shield volcanoes. A lot of you have probably heard that the Himalaya mountains are quite large, and that Mount Everest is one of the tallest mountains in the world. It is. And it is the tallest mountain in the world above sea level. But if we were to go to the bottom of the big island of Hawaii, from the bottom of the ocean where it first starts to form, and we go to the top of the Hawaiian Islands, the top of Hawaii, it's actually larger than Mount St. Helens. It would actually, not Mount St. Helens, but Mount Everest. It actually dwarfs Mount Everest. So here we can see a shield volcano. So again, if we look just above sea level, yeah, it's not that tall. But we actually, if we go down to the bottom of the crust, the bottom of the ocean floor where it starts, it's actually a very, very, very large volcano. Now, when we talk about how explosive an eruption is for volcanoes, we really need to consider two factors. One of those factors is gas and water vapor. And there's a lot of dissolved gases, there's a lot of dissolved water in magma. And think of it as being like a soda. If we took a soda, and if I don't know, maybe you've done this, have you ever taken a soda and shake it up and then give it to someone to open? What happened when they opened it up? Soda comes flying everywhere. Now, if you look at a plastic bottle of soda, you can shake it up and you don't see all those bubbles while the cap's still on. But once you open the cap of a bottle, everything flies out. And that's because while the soda top is on, the gas in the soda is under pressure, so it dissolves in the rest of the soda. But once you release the pressure, that's when the gas escapes. And that's what happens with volcanic eruptions. A lot of times when that magma finally reaches the surface or close to the surface, so much pressure has been released that all of a sudden this gas just explodes out of the magma, the lava, and you have a major eruption. One of the other types of factors that will determine how explosive volcanic eruption is the type of lava. Basaltic lava tends to be more fluid, has very little silica in it, versus granitic, which tends not to be fluid. It tends to be really chunky and thick. And as a result, granitic eruptions tend to have a more tend to be more explosive, just because it is so much thicker. So here you can see eruptions. In eruptions, volcanoes are able to put pyroclastic material way up into the atmosphere, and a lot of times when you get it high enough into the atmosphere, the winds can carry it all over the planet. Now there's three major types of lava. There's basaltic type lava. This is the same composition as the oceanic crust. It tends to form shield type volcanoes. Has silica content, silicon dioxide contents of equal to or less than 51%. Now a different type of lava is granitic or rhyolitic lava. Same composition as the continental crust. This tends to have a lot more silica. Typically it's greater than 67% silica. Now this lava can be pretty hot. It tends to be anywhere from 650 to 800 degrees Celsius, where your basaltic type lava tends to be the hottest lava at about 1,000 to 1,200 degrees Celsius. Now this type of lava tends to be your chunkier lava. And then finally we have the andesitic type lava. This it's your in-between lava. Usually has silica content between 52 and 66%. And as far as temperature, this type of lava is somewhere between 800 and 1,000 degrees Celsius. So the amount of silicon dioxide is in between granitic and basaltic, and the temperature is in between as well. The andesitic tends to form composite type volcanoes. Now overall, about 90% of all lava is basaltic or andesitic, which is good because these tend not to be as explosive as your granitic type lava, and only 10% are granitic or rhyolitic. So here's a quick question for you. Which type of lava would you likely find on a volcano erupting in the middle of the ocean? If you answered basaltic, you're correct. Now if I ask you this question, which type of lava would you most likely find in the middle of a continent, far away from the ocean? If you had mentioned granitic, you are also correct. Good job. Now let me quickly talk about the VEI, because it's going to come up in one of the labs or activities that we do. Volcanic Explosivity Index is a VEI. When we looked at volcanoes, they're going to rate how large the eruption is. And we use ratings all the time. Hurricanes are rated. Tornadoes have a rating. So we're going to rate these as well. The range is typically from 0 to 8. And the higher the number, the more explosive the eruption. So over here on the side, we can start to see that Mount St. Helens, May 1980, was somewhere in that 4 range. Now, was that large? Yeah, it was large compared to some other ones. However, when we get to the Yellowstone caldera, now all of a sudden we're looking at some volcanic eruptions that are in that 7 to 8 range. We're talking about a lot more material, a lot more powerful eruption occurring. Lava flows are streams of molten rock that pours or ooze from an erupting vent. Now, when we look at the lava flow here in this picture, it almost looks like a river, and it is. It's just a river of molten material. And here, first of all, let me just mention that the arrow is actually pointing to geologists. There's a geologist out there doing some research. And here you can see the lava flow just working its way around. Now, basaltic lava flows only a few miles an hour, so it's not like you're going to see one coming at you and you're not going to be able to get out of the way. You should be able to move fast enough. However, it can actually flow for many, many miles. So it doesn't go very fast, but it can actually flow for more than 100 miles. Now, granitic lava, because it's so thick, it doesn't flow very well, and it tends to pile up at vents. And you can actually have things called a lava dome. And sometimes these lava domes collapse on top of a volcano, and they can flow down the sides of the volcano. And these lava domes that have collapsed have been known to travel more than 100 miles an hour. So this is not one of those things you want to get caught in. You're not going to be able to outrun it. And it can actually travel up to 10 miles. Now we're going to talk about a couple different types of lava. And the first type of lava, and I'm talking about lava flows, and is aa. This is a Hawaiian term, and it's a term used for lava flows that tend to be chunkier. Some people theorize that the name aa got its name because this tends to be chunkier material. It tends to be more sharp and jagged. So some people theorize that it got its name aha from the sound that you would have if you were walking over this barefoot. Not that it's hot and burning it, but it would be sharper. So as you're walking over, you'd be going ah, 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 ah. So just a side note there. So here we see an lava flow. It's not going to be moving very fast. It's not like you're going to look one way across the street, another way across the street, and as soon as you step your foot out, wham, you get hit by it. You're going to see it's coming. It's very slow moving. This is the actual type of lava flow that they had in Iceland. People always talk about, well, why don't we just dump a lot of water on this? Won't it stop the lava flow? Well, it's not that easy. The only known time they've been able to stop a lava flow was in Iceland, and they dumped tons and tons of seawater on it. And it was a more slow-flowing lava flow such as this, made up of type material. Now, the opposite of is pohoihoi. Again, it's another Hawaiian term, and when we look at this lava, it's going to be more ropey. It's going to flow faster. It's going to flow easier. And a lot of times, lava will start out as pohoihoi, but towards the end of the lava flow, it's more of your as it starts to cool off. So here we can see and pohoihoi together. And one of the chief threats of lava flows is things burning, things starting on fire. So here you look at a nice restaurant. Here it is. Doesn't look the same, does it? Well, look at the lava. You know, I could ask you to look at this lava and you see how like shiny it is. This is your pohoihoi lava flow. Now, one of the interesting things about volcanoes is, yes, they can destroy, but they can also build. Here's new land that's being created, and that's called a lava delta. So it's actually creating new land. Now, we're going to end by talking about different types of material that's put out by a volcano. Now, Tephra is just a general term. It's a generic term used to talk about the fragments of volcanic rock and lava, regardless of their size, that's blasted into the air by a volcanic eruption. Now, when you look at this poor guy, you can see that this landed on his foot, and he's trying to figure out how to get it off. This is called a volcanic block. These are large pieces of tephra that have been blown up. So imagine if this landed on your foot, or if it landed on your head, you're probably not going to survive. Now, volcanic bombs are tephra, which erupt as lava, and they begin to cool as they fall. So they might come out as molten material, but they fall as solid rock. And some of these can be as large as, an apple, an orange, even a grapefruit. There's a penny in there to kind of give you some size perspective. And so here you can see that it's coming out. It's kind of a neat photo where it's all molten material, and as it comes up, it cools off, and by the time it lands, it's solid rock. So here it is in Iceland. Of course, I hope there's no one living here right now. I'm sure they've abandoned the place. And ash is the smallest fragment of tephra. And here we can see even the ash has different size ashes. So it's pretty small. It's going to easily be distributed by the wind system and by the atmosphere. So if this gets blown into the atmosphere because of a major volcanic eruptions, it's going to travel. Here's an interesting, have you ever been to, Crater Lake National Park? This is actually an ancient volcano called Mount Mazama. And Mount Mazama blew its top a long, long time ago. And what happened was eventually here you can see a caldera was created. And a caldera is created when you have an eruption and the magma, the lava that's inside the volcano or on top. The lava, I guess it wouldn't be called lava, I guess it would be called magma. It's inside the volcano. Once it recedes back down into the lower parts of the volcano or drops, the top of the volcano will collapse. And it creates a huge, usually circular depression called a caldera. And this was Mount Mazama. It blew a long time ago. This is in Oregon, not the city, the state. And this island right here is called Wizard Island. And what happened with the top of this caldera is over the years it actually is filled in with water, and it's actually pretty clean water. And when we look at how tall or how deep it is, the caldera itself is about 2,148 feet deep, or about 655 meters. But the lake itself is a little over 1,900 feet, or at least the deepest part of the lake is about 1,900 feet. I think the average is about 1,400 feet deep. So it's a very, very, very deep lake. One of the questions kids will often ask me is, are there fish in there? Well, fish aren't native to this, but in the late 1800s, they did begin to stock this with fish and introduce fish, and there still are a couple species up there today that are surviving. If you've ever been to Devil's Tower in Wyoming, this is part of an ancient volcano. And columnar, this is columnar jointing. And what happens with this is lava cools. It's going to start to contract, and as a result, vertical cracks form. And they basically, I'm not sure if well, you can tend to see some pictures here. And if you saw some pictures, you can kind of see it right in here. They actually form various shapes. Not necessarily various shapes, but they form a very peculiar shape. It's a hexagon. And that's because it's that 120 degrees, again, that we've talked about happening a lot in nature. So it's rather interesting how these cracks form in the different shapes. And we look at the size of these various rocks. Some of these boulders that are down here are actually larger than, say, a minivan. They're huge rocks, so I don't think you'd ever want to be underneath one of these when they would fall. But Devil's Tower is a very popular place for rock climbers. One time I was there, there's rock climbers all over the place trying to make it up to the top. And we're going to end today just by going over a little bit of vocabulary. Batholith is a huge, massive igneous rock that forms deep in the core of the mountain range. Now, not all batholiths are going to form volcanoes. Sometimes you're just going to have a batholith and the lava doesn't make it to the surface, or the magma doesn't make it to the surface of the earth. These batholiths may cover a few thousand square kilometers. They're huge. Now, a sill is a horizontal magma flow that hardens between layers of rock. So usually it's going to be parallel to your rock layer. So if here's a rock layer, here's your sill. So they're still going to form an igneous intrusion. Now, the opposite is a dike. And a dike is a vertical magma flow that hardens between rock layers. So it's actually going to go through rock layers, and it could separate rock layers, but it bisects them or intersects them. So your sill is horizontal or parallel to the rock layers, where your dike is vertical and it's almost perpendicular. It doesn't have to be perpendicular. Obviously this one's not right here perpendicular, but it's more of a vertical segment. Now, the last thing I'd like to talk about is a laccolith. And a laccolith is basically a mini batholith. And laccoliths, they can be a few meters large, or they can actually get a lot larger than that. Just one more thing about a sill. Sills, some people ask, well, how large do these sills get? Well, they can range anywhere from a few centimeters to hundreds of meters to perhaps a kilometer or so wide. And a lot of times what will happen, if you have these underneath the surface like this laccolith, weathering and erosion will take away the land on top. So, and these might actually be exposed. And a lot of people look at that, oh, igneous rock, there must have been a volcano here at one time. Well, there wasn't really a volcano there. There's igneous material that formed underneath the surface, but weathering and erosion removed the land on top of it. Now, I apologize for these notes. They're a little bit longer than I was hoping to go, but as I said in part one, there really was no good place to cut this in half to make each one about 15-20 minutes long. So these notes are approaching 30 minutes, so I'm going to end them right here. As always, if you have any questions, concerns about the notes, about any of the material, please just ask me when you get to class. Thanks.